Hello, Physics 30s. In today's lesson, we are going to get into the last section of the course, where we're going to start to examine a branch of physics that is referred to as particle physics. And our learning outcomes are to, one, explain qualitatively in terms of the strong nuclear force why high energy particle accelerators are required to study subatomic particles, and two, explain how the analysis of particle tracks contributed to the discovery and identification of the characteristics of subatomic particles. Okay, so what exactly is this branch of physics known as particle physics? Well, it's all about identifying what kind of particles are elementary. When I say elementary, I mean they're building blocks. So like when we take like an object, like what's the smallest building block that we can break it down to? At this point in the course, there are four particles that we can identify to be fundamental. So we know that within the nucleus, we have protons. Okay, can't seem to break those down. We have neutrons. We have electrons. And we also have, from the last lesson, I'm talking about beta negative and beta positive decay, we have the neutrino. Albeit the proton, neutron, and electron, those are the big three. It turns out only two of those four are actually fundamental or elementary particles, and we'll get into more about that in the next few lessons. But that's what we're going to try to examine. We're going to try to examine like what are our fundamental building blocks. Now, to answer this question, which particles are fundamental, physicists need to make use of high energy particle accelerators. What do we do with a high energy particle accelerator? Well, we take certain particles and we fire it at different nuclei. Okay, so I'm just going to sketch a little picture here. So I'm going to draw a circle, and I'm going to call this the target nuclei. This target nuclei would be large, and it's most likely going to consist of a bunch of protons and neutrons. I'm just simply going to show the protons that make up the target nuclei. What we're then going to do is we're going to take another particle, which I'm going to call a probe particle. And I'm going to fire it at the target nucleus. Okay, so why do we do this? One, it allows scientists to probe the structure of the nucleus. I suppose probe would be identifying like something possibly about like what the nucleus is made up of, and we could know that based on how the probe particle interacts with that target nucleus. Like, you know, it could be a matter of measuring like how much it deflects when fired at like certain angles, something along those lines. But two, the thing we're more interested in is if we take a probe particle and fire it at a target nuclei, we can actually create new subatomic particles. Because what's going to happen is when this probe particle hits this target nucleus, it's going to cause it to split. And when it causes it to split into like these two parts, like part one and part two, there is also the possibility that you could get a third part, like maybe like a third particle, a third new particle. So I'll call it just a new particle. Now, there's a couple of problems with this. So first of all, this probe particle needs to be really, really, really high energy. The reason being is, well, first of all, I said it needs to overcome the strong nuclear force. I haven't really defined the strong nuclear force yet. And again, I'll do it in like much greater detail in the next lesson. But one of the biggest problems is that initially, like if you're firing a probe particle, if this probe particle is positively charged, it's unlikely it could ever interact with the target nucleus because the repulsive force would just push it away. However, we could fire a neutron, which has no charge at this target nucleus, and we could cause it to split into a couple of different pieces. Now, I said it needs to overcome the strong nuclear force. The strong nuclear force is kind of like the glue that holds the nucleus together. It's really, really strong at very small distances. So this target nucleus would have a strong force that's kind of gluing, holding the target nucleus together. In order to make it split into these two pieces, these two daughter isotopes, 1 and 2, you'd need this probe particle to have a lot of energy, enough energy to overcome that strong nuclear force that's trying to keep it glued together. The other thing is that if I have a probe particle that has really, really high energy, I might be able to create mass from it. So think of it like this. This probe particle has a lot of energy, delta E, which is kinetic energy specifically. And what we want to do is we want to turn this energy into mass. We want to make a new particle, or try to make like a new particle. So according to Einstein's mass energy equivalence, like perhaps if the probe particle has enough energy or kinetic energy, maybe by firing it at a target nucleus, I might be able to take that kinetic energy and form matter out of it, which would give me a new subatomic particle, and potentially that particle is also elementary. And again, that's just according to Einstein's mass energy equivalence theory. These particle accelerators are humongous. So this is like an aerial view of the Tevatron synchrotron at the Fermilab near Chicago. Basically, I'm just going to focus on like the size of one of these tracks here. So I'll highlight it. So you can see like there's like these large circles that go like all the way around. I'm not sure what this circle has specifically in it, but like the key thing is that you need to be able to get your probe particle so it has a really, really, really high kinetic energy. So what these particle accelerators do is they're attempting to take your probe particle and to make them move ridiculously fast. So I suppose one way we could do this is we could have a bunch of like parallel plates, like one after another, after another, after another, after another, where the parallel plates are constantly accelerating your probe particle to a higher speed. Now that would require my probe particle to be a positively charged particle. But again, if the charged particle is has a high enough energy, I think it can at least overcome that electrostatic repulsion. Although I think the probe particle, if it's positively charged, you don't want it to be large. Like even something like an alpha particle, a probe particle is probably too big and has too much charge to actually hit that target nucleus. But anyways, the idea is you need this huge distance to try to accelerate these particles over. I mean, this is like probably like kilometers like long to accelerate it so your probe particle has a really high speed, and a high enough speed where maybe you have enough kinetic energy to turn to form new matter. And it turns out when physicists do this, there are new particles you can produce. This is often referred to as a subatomic zoo of particles. And this chart is going to be really confusing. I mean, I'm not going to explain it just quite yet because it breaks it into a bunch of different families like leptons, mesons, baryons, and hadrons. We'll worry more about the classification of the families in the next lesson. I'm just simply trying to point out that when we do this, fire high-speed probe particles at a target nucleus, we can actually produce a subatomic zoo of particles. Some of them might be fundamental, others not so much. But let's give an example, a more specific example of how we can produce this. So how could you actually take energy and get matter out of it? One thing you can do is you can take a high energy photon. So high energy photon would be a gamma ray photon. Okay, that's at the top end of our electromagnetic spectrum. So your probe particle would actually be a photon. And we fire that probe particle at a target nucleus. And it turns out when we do this, we can actually get an electron-positron pair. So we're taking our photon energy and we're getting mass out of it. We're getting the mass of an electron and a positron. Because we're going from, in this pair production, we're starting with energy and we're getting matter out of it. It's an energy to mass conversion. Okay, let's write down an equation to represent this. So we take a gamma ray photon, which has no nucleons and it has no charge. We fire it at a target nucleus, and when it hits this target nucleus, we actually produce a positron, which is 0 plus 1 beta, and an electron, 0 negative 1 beta. So the idea is I'm taking all of this photon energy, so this would be delta E, and I'm converting it into mass. I'm getting mass out of this interaction. You do need to fire it at a target nucleus, though, because if you didn't fire it at anything, then the photon would just keep doing whatever it's doing. But by firing at a nucleus, perhaps we can initiate some kind of a nuclear reaction. Okay, that's called pair production. The pair we're producing is the pair of the positron and the electron, same mass, opposite charge to it. The reverse process is called pair annihilation. So in pair annihilation, we're going to take mass and we're going to turn it into energy. Anytime you have a particle that meets its antiparticle equivalent, and I briefly discussed this in the last lesson when I was trying to define what an antineutrino is. So if you took a neutrino and it met an antineutrino, it would actually annihilate to give you a pair of gamma ray photons. So this time you're going from mass into energy. In fact, in this pair production, when we actually get a positron and an electron, that's a matter and an antimatter. They would annihilate pretty quickly to give you a pair of gamma ray photons, unless you find a way to separate them. So the pair annihilation equation would look like you have 0 plus 1 beta, which is a positron, plus 0 negative 1 beta. So a positron meets an electron, and it produces a pair of gamma rays. Now, the question immediately is, you might be thinking of is, why is it a pair? Why can't it just be a single gamma ray? Okay, so this is going to deal with a different physics principle. So let's say that we have a positron, E plus, and an electron. They both have the same mass, and let's say they're going to hit each other at the same speed. If you were to calculate the net momentum of this collision beforehand, if these both have the same mass, and they have speed or velocity in opposite directions, your net momentum before, sigma p before, would be equal to 0. Momentum is something that is conserved during a nuclear reaction, which means that the net momentum after should also be equal to 0. Now, if you just got rid of one of the gamma rays, let's say that this gamma ray didn't exist, then you would have no momentum before, and you'd have momentum towards the right after. So that defies conservation of momentum because you're actually gaining momentum in a particular direction. By having a pair of gamma rays, well, this gamma ray would have momentum towards the left. This one would have momentum towards the right. Because momentum is a vector quantity, those two momentum values would cancel off to give you a net momentum of nothing. This pair annihilation explains why antimatter doesn't really exist in nature, not in like a natural setting anyways. In like a controlled lab setting, we can get some antimatter, but otherwise not so much. Because the problem is, like, just think about this, in the pair production, so great, we go ahead and we fire a gamma ray photon at a target nucleus, and it produces a positron, and it produces an electron. But that's a matter and antimatter, that's a matter and antimatter pair. So immediately they would just hit each other and then go right back into energy. So this is why, like, we don't really observe antimatter in nature, because it wouldn't take very long for it to meet its matter equivalent and then annihilate back into energy again. Okay, so I've mentioned that we have this entire subatomic zoo of particles that we can get by like firing a probe particle at a target nucleus, and as long as its energy is high enough to overcome the strong nuclear force, we could potentially get new matter. The next problem is, well, how do you detect this? Like, how do we even know we're producing new types of matter. Well, there's a couple of devices we can use to observe this. These devices, which I'm going to go through right now, are referred to as a cloud chamber and a bubble chamber. So we'll start off with a cloud chamber. Okay, this is like a really complicated picture. So let's just try to simplify it. Okay, so what exactly is a cloud chamber? A cloud chamber is just, you have a chamber. So I'll highlight it in red here. So let's say we have our chamber. And inside this chamber, we have a gas. Typically it's an alcohol that is in its gaseous form. So one example I can think of is ethanol. So I think ethanol has a molecular formula of C2H5OH. If I recall my organic chem like somewhat correctly, I think ethanol is C2H5OH. Okay, so in this chamber, I have a bunch of an alcohol, but the alcohol is in its gaseous state. When we fire a subatomic particle through this cloud chamber, what happens is, so here's where I'm firing my subatomic particle in at this location. So there's some kind of nuclear reaction that's occurring there where I'm hoping to produce a new subatomic particle. When this subatomic particle is produced, what it'll do is it moves through the chamber, and as it moves through the chamber, it condenses the gas. So what it does is it turns the gas back into a liquid. So as the particle moves through the chamber in this line, behind its path would be a bunch of little tiny droplets of water. So I could just illustrate them with a different color. So we see like a little trail that follows behind, a little liquid trail that follows behind. The analogy I like to use here is what we're observing is we're not directly observing the particle, we're just observing its wake. So think of like a motorboat that's like just moving through the water, and behind the motorboat is the wake. The wake is just it's evidence that the motorboat has disrupted the medium of the water. So essentially the same thing's happening here. You can think of the boat as being the subatomic particle, and as the boat goes through the cloud chamber, the particle goes through the cloud chamber, it's disrupting the medium. And specifically what it's doing is it's causing the medium to condense and give you this liquid trail. Now, I'm going to give a bit of an explanation as to why this happens. I don't know if this is the complete correct explanation, but I asked Miss McRory about what she thought would be a good explanation for how a cloud chamber works, and this is what I got, okay, and I trust her. Okay, so for a cloud chamber, let's say that we have this cloud chamber is made up of ethanol. So ethanol, we'll draw a few of these molecules here. So we'll say C2H5OH, 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 C2H5OH. Now, apparently ethanol is polar. And in terms of what it means for a molecule to be polar, it means that one part of it has a partial positive side. So I'm going to use this symbol to indicate partial. So here's my partial positive side, partial negative side, partial negative side, partial positive side, partial positive side, partial negative side, partial negative side, partial positive side. Okay, so that's my cloud chamber that has ethanol in a gaseous form. Now let's say that we fire a particle or target nucleus and it does produce a new subatomic particle. Okay, so let's see what happens to this subatomic particle. So I'll go to, let's do green here again. Okay, so here's my subatomic particle that's produced. I'll say it's positively charged and it's going to zoom through this chamber. Okay, so it zooms through this chamber. Now, what's that going to do to the actual ethanol vapor? Well, because the ethanol vapor is polar, it's going to have an effect on the molecules. If this is positively charged, I'd expect let's go to blue here. I would expect the partial negative parts to get attracted to the proton. So what happened is, as this guy zips through these, oops, I wanted blue. That is blue. Okay. The partial negative parts are going to get attracted to the positively charged particle. When these polar molecules come closer together and there's less space between them, they undergo a phase change. So specifically what's happening in the cloud chamber is, as a result of the subatomic particle going through the chamber, it causes a phase change where you go from a gas to a liquid. And that's why we're observing all of those liquid trails that are following behind. It's the wake that follows behind the subatomic particle as a result of those polar ethanol molecules that are coming closer together. Okay, so that's how we can observe the existence of a subatomic particle. We just see the evidence of the wake that it leaves behind. Another chamber is a bubble chamber. A bubble chamber contains, instead of ethanol gas, a bubble chamber contains a liquid, specifically liquid hydrogen. Hydrogen at a very, very low temperature, negative 252.8 degrees Celsius. That is the temperature where I believe if you even increase the temperature slightly, it'll go from hydrogen being a liquid back into a gas. So we're kind of at the threshold where we've just got the hydrogen at a liquid. And then what we do is we fire a subatomic particle, or a photon actually, this could work too, through the chamber. And once again, this new subatomic particle disrupts the medium. So by disrupting the medium this time, it causes a phase change where you go from a liquid to a gas. Okay, so let's give a bit of a chemistry explanation for how this one works. So let's say we have hydrogen. So hydrogen is diatomic. So we have H, and I'll show the bond that just forms between them. We're going to fire a high energy particle or a photon. Okay, it can be one or the other. The important thing is that it's just high energy. So we have a high energy particle or a photon. So let's do a particle here. Here's my new subatomic particle, and it's going to hit this bond. Now, if it's high enough energy, this particle can cause the bond to break. And if the bond breaks, you're then going to get two ions. You're going to get the H plus ion, and you're going to get an H negative ion. H plus ion just means it's hydrogen that's lost an electron. H negative would be hydrogen where it has gained an electron. Now, apparently, so after this happens, the subatomic particle comes through, it breaks this bond, and then it zips away. So it just keeps going away. Well, this positive and this negative end, they attract, and they want to reform the bond. When they reform this bond, what I've been told anyways, is that in the process of reforming this bond, this is an exothermic reaction. An exothermic reaction releases energy to the surroundings. So the surroundings would be the bubble chamber itself. So by your high energy particle going through, it breaks the bond. And when the bond reforms, it transfers energy to the rest of the chamber. And that actually heats the hydrogen up. And that's going to cause heats the chamber up. And that's going to form some bubbles. So if you go from a liquid to a gas, you form bubbles within the liquid. So once again, we're just getting a wake that kind of follows behind the actual subatomic particle just to prove its existence. Now, I just did want to point out one thing, though. For a cloud chamber, I believe this only works for detecting charged particles, because in order for the polar alcohol to come together, you need the subatomic particle to be charged. So it must be charged for these guys to come together. For a bubble chamber, you don't need that criteria. The only thing that matters for a bubble chamber is that this subatomic particle has high enough energy to break the bond. Whether it's charged or not, it does not matter. Okay, it's as long as it has a sufficient energy to break the bond in the first place. And again, in a bubble chamber, it's just the reverse phase change from a cloud one. So cloud one, we had a phase change from a gas to a liquid as a result of the alcohol getting condensed. In a bubble chamber, we're going from a gas, liquid to a gas, other way around. This one, we're going from a liquid to a gas as a result of the hydrogen being heated, which is what happens due to the exothermic reaction. And again, we're at that threshold that if we heat up the hydrogen even slightly, it's then going to turn to a gas and we get bubbles that follow behind. Now, we want to know a little bit more about what kind of subatomic particles we're producing. So all the cloud and bubble chamber right here would prove is just that, yes, you're making a subatomic particle because we see the evidence in the wake that follows behind the particle. But what if we wanted to know what the charge of the particle was? Well, what we could do is we could subject the bubble or the cloud chamber to a magnetic field. By subjecting the bubble chamber to or cloud chamber to a magnetic field, we can actually figure out, one, what is the charge of the particle based on like what direction the particle deflects, and two, we can also do a calculation for the charge to mass ratio of the particle. Okay, that picture is kind of confusing. I have a better one. Okay. When I say better, that's like a very, I shouldn't say better. The pictures are awful, okay? This one is less awful. Okay, so in this one, this point right here is kind of like where I have my target nucleus. So I fire a probe particle at that target nucleus, and what I start to observe is a bunch of spirals in the track. So I get like a big spiral that kind of does, so let's just do this. Get this really big spiral. Okay, that's one spiral, and you also get a second one that kind of goes down here. I'm not tracing it exactly. Okay, so we're getting two spirals, which means in this situation, you've actually created two subatomic particles. Now, depending on what direction the particle goes, we can actually figure out whether it's a positive or a negative charge. And you can just use it according to the hand rule. So in this situation, I'm not going to go through all the work for it, but if I want to like identify a bit about the hand rule here, so it shows an X, which I believe is a reference to the magnetic field. So your magnetic field is X, which is into the page. We'll assume that the target nucleus is right here, and we're firing our probe particle in this direction. So that would be the velocity of my charged particle. And when the track, after they're produced, they initially, before they deflect, they do go a little bit towards the left first. In the top situation, you'd have a magnetic deflecting force that would point towards the top of the page. And in the bottom situation, you'd have a magnetic deflecting force that points towards the bottom. So now it'd be a matter of just identifying, well, which hand can actually correspond to which track. Okay, well, let's see what happens if you use your right hand. If you take your right hand and you point your fingers into the page, and again, keep your thumb perpendicular to your fingers, and if you have your thumb that points towards the left, my palm needs to face, so if my thumb is towards the left and my fingers are into the page, my palm must face down, okay? If my palm faces down, and I'm using my right hand, that means that this bottom track here would actually be a positively charged particle. On the other hand, literally, that's like one of the worst jokes in physics that Mr. Stallrate and I like to use. See, it's funny because like we're literally using the other hand now to like, okay, I'll stop. Okay, so if you take our left hand and I point my fingers into the page, and then you take your thumb and you point it towards the left, your palm then faces towards the top of the page. Since you have a deflecting force towards the top of the page, that would tell me that this is actually a negatively charged particle. As for the charge to mass ratio, back in the lesson on the mass spectrometer, I believe we derived an equation that looks something along the lines of R is equal to mv divided by Q times B. It might have been in a different format. If you take that equation, you can manipulate for Q over M. So you'd have Q over M is equal to, I think it'd be V over RB. So if you know the radius of deflection, which we could measure, I mean, it's changing, but we could measure the initial radius of deflection. If you know the magnetic field intensity, and if we know how fast the particle is moving, which I suppose if we were just observing how quickly the bubbles form, which is probably really quickly, we could get it. We could also get the charge to mass ratio. So again, we get two things. We could figure out the nature of the charge, whether it's positive or negative. We could also get information about the charge to mass ratio of the particle. I mentioned here that this is essentially the procedure that a scientist named Carl Anderson used to prove the existence of a positron. So I believe what they would have done is they would have taken a gamma ray photon, fired it at a target nucleus, and we would get a couple of spirals that look like this. Although the size of the spirals it'd be perfectly symmetrical if you get a positron and you get an electron. And this would be a way to prevent the positron and the electron from hitting each other and annihilating right away. Because if you put in a magnetic field, they're going to separate right away, as opposed to keep going in a straight line and then annihilating. Now, just a couple other things about the tracks here. So you'll notice that the track it's spiraling. Okay, it's not just like a continuous circle; it just keeps going round and around and around. The radius keeps getting smaller and smaller and smaller. So you have any idea like why that might be the case in terms of like why it's spiraling inward? Well, there could be a couple of explanations. One would be if it's a charged particle. Remember, charged particles that accelerate, they emit electromagnetic radiation. So if that charged particle is continuously emitting electromagnetic radiation, then it would lose energy in the form of kinetic energy. So it would slow down, and that would result in a decreased radius. But no matter what, your speed is going to decrease. If you produce a subatomic particle, it still has to plow its way through the rest of your cloud or your bubble chamber. So just by interacting with the medium is going to slow the particle down. If it slows it down, it loses speed, and then it's going to cause the radius to get smaller and smaller and smaller. The other one I wanted to point out is you'll notice like off like the primary spiraling track, there's a couple of like little mini spirals. They're like almost like these secondary ones that sit off the track here. In terms of what these are, these would just be, I would say these tracks are formed due to secondary collisions between the particle you produced and another particle in the chamber. So within the chamber, there could be another particle that's just sitting here, maybe like a positively charged particle at rest, and it's content sitting there. But once you produce a subatomic one, it starts spiraling around and then it nails that guy. Then once it nails that guy and gets it to move, well, it spirals a little bit too. So it would just be due to a secondary collision between the subatomic particle you make and another particle is just sitting in the chamber that causes that particle to then spiral, because then it picks up speed. And as long as a particle is moving and it's charged in a magnetic field, it does get a little bit deflected. Okay, quick example. So I've said, calculate the minimum frequency of a photon required to produce a stationary electron-positron pair. Okay, so we're producing an electron-positron pair. So that is pair production. What are you doing in pair production? You're taking a gamma ray, which has 0 nucleons, no charge. You fire it at a target nucleus, and then that produces an electron. So that's 0, -1, beta, and a positron, 0, +1, beta. And what it wants to know is what's the minimum frequency of my photon that would be required to produce the electron and positron, assuming they're not moving. Okay, so we're just giving it enough energy to produce the pair, but not to actually give it any kinetic energy to move it. Okay, so what's happening here is we are taking photon energy and we are forming mass. So we're getting delta M out of this. So let's use Einstein's mass equivalence theory to do it. So we'll say delta E is equal to delta mc squared. So the c squared is that conversion factor between the mass and the energy. Now, what's the energy it's being provided? That's photon energy. So E photon. What mass are you producing? Well, you're getting the mass of an electron, so mass of E negative, and you're getting the mass of a positron, C squared. However, we know that both a positron and an electron have the same mass. So let's just write down, but Me negative is equal to Me positive. Okay, so let's simplify the equation. What's the photon energy in terms of the frequency? It would be HF is equal to, well, if they both have the same mass, the mass of an electron plus a positron would just be 2 times the mass of an electron multiplied by the speed of light squared. Okay, so let's calculate what the frequency is. So frequency would then be 2 times the mass of an electron times c squared, all divided by h, which is Planck's constant. Okay, let's plug the numbers in now. So this would be F is equal to 2 times the mass of an electron, which is 9.11, times 10 to the negative 31 kilograms, multiplied by the speed of light squared, 3.00, times 10 to the 8. Man, I hate using a drawing tablet. I cannot wait until I can write on a whiteboard again. Okay, not to mention this drawing tablet is just awful compared to my other one. But at least this one doesn't do the horizontal lines out of nowhere spontaneously. Okay, 6.63 times 10 to the negative 34 joules times seconds. And this is going to give me a photon frequency that is, let's calculate it, 2 times 9.11, 10 to the negative 31, times 3 second exponent 8, all squared. Divide this by Planck's constant, 6.63, 10 to the negative 34. And we're going to go to 3 significant digits because of all of our experimental speed of light is 3 SDs, Planck's constant 3 SDs, mass of an electron 3 SDs, and I get 2.47 times 10 to the power of 20, and the units are hertz. I should point out that that's in the gamma ray photon range. So if we look at the way I always remember it is, I think visible light, I just memorize that one as being 10 to the 14. And then when you go up to UV, you just increase the exponent by a power of 2. So UV would be 10 to the 16. And then you'd have, so VL, UV, X-ray would then be 10 to the 18. And then gamma ray would then be 10 to the power of 20. And odds are, if you're going to make mass out of energy, you need to use the highest energy photon you can possibly get. Now, just a bit of a warning, if you had to do the reverse process where you had to do pair annihilation, so pair annihilation, is where you would take electron, positron, but this time around you get 2 pairs of gamma, or you get a pair of gamma ray photons. The reason I'm warning you about this is just be aware that when you get pair annihilation, whatever energy, so here you'd be going from mass into energy, just be aware that the energy that's being produced from the mass has to be split between these 2 photons. So it's not going to a single photon. As for in the pair production, we were just taking energy from 1 photon. We only needed 1 photon for pair production to occur. Okay, so the assignment is going to be to start the particle physics Handon assignment. Now, there are a lot of questions on the assignment that deal with the next lesson on quantum field theory, but you can get a good start on the assignment, like at least the first page and I think the second page, and kind of get into a bit of the third one. And then after we do the next lesson, you'll be able to complete the remainder of the particle physics hand and assignment. And I'll talk to you about that lesson next time.